Thanks everybody for joining my talk this afternoon. I will share with you today how we as economists see the challenges that climate change poses for economic systems. When we talk about climate change, we typically tend to think along two lines. One is mitigation and the other one is adaptation. So today I will talk about both. Most of the time I will spend on mitigation, meaning that we would like ideally to progress from the situation here on the left to something like this here on the right. This is also called decarbonization, or sometimes it is also referred to as decoupling. So who is our couple that we would like to divorce as soon as possible? Let us look at some facts and figures. Well, of course, it is the world gross domestic product on the one hand. The real GDP has increased dramatically over the last 500 plus years. The real GDP per head increased just as much, and here we are talking about something like 70-fold. And this is in spite of almost exponential growth of population over the same period. Now, think that all of this is happening on our finite planet. Here we can already sense that we may see some challenges coming with if we continue in the same way. But on top of that, there is another problem, which comes here. The second half of this couple, the CO2 emissions. We all know that emissions have risen quite a bit over the last 30 years. Here, I show you on the left side the graph starting at 1990, and we see that they increased almost twofold. But this is a global trend. If we look more carefully at different world regions, and if we use emissions per capita, that is to say emissions per head, we see a different picture. Well, some regions of the world are high emitters, although they are doing better over the last, say, 5 years. Then there are other regions who are kind of flat, like the EU, and also declining a bit. And then there are others which are increasing their emissions per capita over the last 10, 20 years, for instance, China. And then, of course, there is climate change. We know that the global average surface temperature is increasing. We know that the sea level is rising. We know that CO2 emissions are rising, and the relationship between the cumulative CO2 and warming is almost linear. I don't know if you can see what's written here at the bottom of this picture, but the question on top is why we haven't been contacted by intelligent life from another planet. The answer is actually given here at the bottom, and it says they saw us first. I kind of like this picture. Now, what's more? Over the last 30 years, climate-driven natural disasters have increased, not only in their numbers, but also their frequency has increased. Different regions of the world have not been affected in the same way. What is really worrisome is that the poor countries have been affected relatively more. So this is a kind of a direct pathway for widening the income gap or widening of the world inequality. We all know that climate change is driven by the accumulation of greenhouse gases. Greenhouse gases stem from the burning of fossil fuels. So let us check what's happening with our fossil fuels. Actually, there is another problem associated with them. And the problem is that they're actually technically exhaustible. For instance, our reserves of oil and gas won't last for more than 50 years. All of these observations bring me to these key questions. First of all, given natural resources are limited, can the world economy grow forever? Secondly, given that burning of fossil fuels leads to accumulation of greenhouse gases and to climate change, consequently, how can we sustain future growth? Thirdly, is it possible to decouple growth from energy use? And finally, what are the optimal policies to mitigate climate change and at the same time to ensure sustained growth? We need to think hard about these questions. And here is a thinker. Originally, this statue was called a poet, but I think it can also be called the doubter. As Voltaire said, doubt is an uncomfortable condition, but certainty is a ridiculous one. So we need to address these doubts, the many concerns, and to get straight messages in our times of information overflow. And then, of course, we need to communicate them, for instance, with people like this. What counts for them? The majorities, re-election, visible action. They do not primarily care about core results of science. How can we reach to these people? How can we frame our wording? And what about the real people? What is more attractive to them? Well, different issues. Of course, alarmism is very popular. Limits to growth, population bomb, environmentalism, degrowth, all these things. But most of all, what counts for them is equity and fairness. So we definitely need to include equity and fairness in our analysis and in our policies. We should also address the so-called Greta's question, if I may call it like that. Why consider marginal changes when carbon emissions are wrong in the end? It is all about the transition, and I will tell you about it in a few minutes. Now, a bit more on facts and challenges. Here is our couple again, the CO2 and GDP. If we look at the top picture, which shows the world GDP with these black squares and the world CO2 emissions over time, we see some kind of a relative decoupling. GDP is growing, CO2 emissions are growing as well, but not as fast. But then at the bottom, we see other examples of some specific world regions. For instance, in UK, Sweden, and British Columbia, we clearly see that GDP is growing over time, while emissions are actively declining. And in Sweden, for instance, this gap is substantial, plus 49% for GDP, minus 25% for emissions. So the challenge is, how do we transpose the results of these guys, these regions, on the world level? This is a big challenge. What about the future development? We know that GDP will most likely be increasing over time. We also know that if we don't do any policy, any climate policy in particular, our planet will be warming. But we can't afford that. We have our Paris Agreement, we have our 2 degrees target, we have our carbon budget. So we need a drastic reduction of our emissions by about the year 2050. So a significant decoupling is needed. Is it ambitious? Is it maybe too ambitious or even impossible? Actually, I'd like to find out your opinion. Now, I invite you to click on this link or simply use the QR code with your smartphone and answer or vote on this simple question. Is it possible to reduce fossil fuel emissions by 50% when in the same time period income rises by 50%? So I give you a minute or two to think about this question and then cast your vote. In the meantime, I'm trying to open the page where we can check the results, which I don't see at the moment. Let me try again. Does it work for you at least? Can you vote? Yes, great. Now I just have to I need to find the right page. Maybe, oh, I know why. I will have to exit the presentation mode temporarily so that I can open the right page in the browser. If that is okay. So I will stop the share. And here, okay. And now this should work. So here we go. So these are the results. Actually, I'm happy that the majority of you are quite optimistic. In fact, I'm asking this question to all of my students. And you know, there is one interesting thing that I notice over time, that when I ask this question to students from, say, second, third year bachelor, they tend to be more pessimistic. The majority says no. And when I ask this question to students from, say, second year master, they tend to be more optimistic. 2/3 will say yes. So I think the more information people get, the more educated they are, the more options they see, the more optimistic they are. So education is key. And I will come back to this point in a few minutes again. Now I go back to my slides. Here we go. So let me now switch to the feasibility. Often when we talk about decarbonization or decoupling, we hear some pessimistic views. For instance, over time, long-run growth in living standards is strongly associated with rising energy use, especially in developing countries. So it sounds like growth is intimately coupled with energy use, and it is impossible to separate the two. Something similar Also in the Malthusian tradition, the Earth can support only a limited number of people in a sustainable manner. Humanity has a clear choice between more people with poor lifestyles and few people with a better quality of life. Then we also see things like this, the famous iPad formula or the Kaya identity. What does it mean? It says impact is equal population times affluence times technology. If I translate this into environmental impact, or say pollution, or equivalently to energy use, we get population times affluence, which is measured by GDP over population, times technology, which is typically measured by the efficiency of resource use, which is resource use over GDP. This is a simple identity, but does it really work? Is it really true? Are things only black and white, or are there some shades of gray? What about all these things? Prices, low demand, input substitution, sectoral change, capital accumulation, risks and uncertainty, diversification, demographic transition, endogeneity of growth, technological change. What about economics in the end? And what kind of economics are we talking about? For instance, carbon prices, they can be different levels. They can have different time profiles, differences with respect to countries. Then we have different economic model specifications. We sometimes tend to think in a static partial equilibrium, which is by far not correct when we're thinking about global environmental change and growth. We have to think more globally in a general equilibrium. Then we can calibrate our models correctly and get the policy prescriptions. We can think about combining different policies. As I mentioned to you already, it is important to consider equity and fairness, and of course, public communication. So here I will show you not only some shades of gray, but also some colors, the key building blocks of economic models or economic analysis. The first one is dynamics. Investments are inherently dynamic. Climate change is also inherently dynamic, so we really cannot do without considering dynamic effects. Then there are different input conditions. For instance, resource depletion, different climate damages, endogeneity of our labor supply. Then there are risks and uncertainties, for instance, associated to environmental shocks, to the arrivals and their severity. There's also policy uncertainty. Then there can be different disruptive development. And there is a large role for expectations, as I will tell you in a few minutes as well. There can be some transition periods. We can even think about fourth industrial revolution. Then there are further issues like non-market effects and meaning of life. And finally, there are, of course, policies. We are concerned about the efficiency, but also about the equity, about the inclusiveness of institutions, but also the effects that our policies can have on assets. For instance, environmental policy can certainly generate some stranded assets. Now let me talk about input characterization. In economics, we typically think that our GDP is produced using various inputs. This is very intuitive. And what kind of inputs do we have? We have capital, like for instance, machines, the physical capital. We also have human capital, knowledge capital, or even health and various infrastructures. Then on the other hand, we also have natural resources like fossil fuels and also renewable resources. And then there are other inputs like labor and land. The nice and interesting thing about all these inputs is that they can be substituted. They are substitutable. For example, we can substitute fossil fuels for physical capital or labor for physical capital and vice versa. So let us look at this graphically. On the vertical axis, you see the output. And on the two horizontal, you see our resources on the one hand and our capital on the other hand. And I'm abstracting from the other inputs for the moment. This is something that economists call a production function. It's typically increasing in both arguments because the more resources we have, the more output we can produce. And the same for capital. So suppose we want to have a constant level of output. That will be represented by a line like this. Now, if we have less resources, what will happen to our output? Well, if the resource input is declining, then we may end up with a declining output if there is no input substitution. But we can very well stay on the same output trajectory or even have an increasing output over time. Let me explain to you how this works. Consider this simple graph. So on the right-hand side on top, you see the resources and capital. It's just what I took from the previous picture, basically a little slice. Here at the bottom, I have resources as a function of time. They are, of course, declining in time. And here on the left side, I have capital, which is growing over time. And here at the bottom, I just have a 45-degree line. So suppose capital is increasing over time. And suppose that it starts to grow even faster along the red line. What does that mean? It simply means that for the same input of energy resources, we can achieve a high level of output. So let me go a bit more into economics now. Consider a two-sector approach, what we call. We have the final output, we have capital accumulation, we have resource depletion, and then we have us, the households. All of these sectors are described by their specific equations, which I, of course, skip for now because that's not really the core. I don't want to bother you with that. The bottom line is that we can express the output growth as a function of our model parameters. So along this line here, the output growth is 0. In this region, the output growth is positive. In this region, the blue region, the output growth is negative. What do you see? Well, the first thing to note is that actually we have good news here. Even though our resources are scarce and declining over time, a positive rate of output growth is still feasible, provided some conditions on the economic fundamentals are satisfied. So this is exactly what we want. This is our decoupling. The output is growing over time, the resources are declining over time. Now, suppose that we cannot substitute capital for resources so easily. That means that our capital resource substitution curve becomes kind of folded, or in the limit, it could even have a kink here. But what does that imply for our capital growth? If we look on the left-hand side now, we see that capital has to grow faster. And that means that poor input substitution can actually support decoupling. This is already very good news. Now let me introduce climate change into this model. We have stock pollution, which is increasing with resource use. What about the damages to productivity or to capital? Most likely to both. Now I'm augmenting my previous analysis with another square here, which represents the dynamics of pollution. I also have to include pollution damages to my capital, for instance, through the loss of infrastructure. Again, I skip the boring equations and go back to my picture. We notice immediately that we have a resource drag here, something here, a term which decreases our output growth. But still, we see that growth is possible, even with climate change damages. It is still feasible. Now, what about climate policy? Suppose we want to limit the stock of our oil, let's say, or coal, even better. That would amount to simply shifting our time path of resource extraction sort of inwards. So now it will be along this green line here. What does that imply for the growth of capital? Well, now we will have to switch to this black line here. Again, capital will be growing faster. There are static and dynamic effects of the climate policy. By static, I mean that the level of our current consumption can be affected. By the dynamic effects, I mean that the growth rate of our consumption can be affected. In a few minutes, I will tell you about the magnitudes. But what is important is that the cost of the policy should not occur in a single period, but better be distributed over time. And that, of course, depends on how we design our policy. Now, suppose we get a backstop technology. By backstop, I mean a perfect substitute for polluting exhaustible resources. If that is feasible, then we can achieve here a complete decoupling. From that point on, we would have perfectly green growth. Of course, backstop is not yet available in general, but in different sectors, we are, or very soon could be very close to complete resource phase out. What about climate shocks? We can also include them. We can include the climate-driven disasters. We can include the tipping point. And the nice thing is that the economy is flexible enough to accommodate all these things. The policy and investments will take these risks adequately into account. In fact, mitigation policy and growth are intimately connected. So it would be wrong to think about growth or growth rate of GDP as something which falls on us from the sky. We, by our behavior, define how we grow. And in the same way, we define our policies, and policy and growth are interconnected. We can also add short-term fluctuations. It will not change anything. As I said, optimal investments and optimal policy will take care of all the risks and fluctuations. Another interesting point on disruptive development and role of expectations. Suppose here we have two stable equilibria. This one is kind of a bad one because here we use a lot of resources and little capital. In this one, we use little resources and lots of capital. But where will we end up? Not obvious. For example, in this region here, which I call the overlap region, both equilibria are possible. And the final outcome will depend on agents' expectations. If agents form correct expectations, they can drive the economy towards the green steady state. But also if they have wrong expectations, they can go to a bad steady state. there is a huge role for policy to form agents' expectations. I give you an example. Many people still prefer not to buy electric vehicles because they are scared that there's not enough infrastructure. It will take them a lot of time to look for a charging station to charge the car, or they will have to charge it at home. There is not enough momentum. But if I know that all my neighbors have electric vehicles, then there is a critical mass, there will be enough infrastructure, and I will have an incentive to adopt electric vehicle as well. In fact, for me, the cost of non-adoption will be way higher than the benefit of adoption. So expectations are important, momentum effects, and critical mass. Now, I haven't said anything about workforce so far. We can add that as well. We can model the labor force, we can include it in our model, and what comes out is actually labor, our ultimate resource, is helping our growth rate. This is exactly the opposite of what Malthusians say. So in the end, population increase helps our growth and can even counteract the resource drag. Of course, education is key. People help growth because they are capable of innovating. We have our brains, we have our knowledge, we can create ideas, and that's how we can help the economy to grow and to grow in a clean way. I can also add innovation. I can also add endogenous fertility decision population. Things become really, really complicated. And of course, I will skip that. I'll show you all these things just to let you know that nothing comes from thin air. We have thought carefully about these things. Then there are non-market effects, which I probably skip, but I will go directly to the numbers, because that is what we are ultimately interested in. What is the effect of a climate policy on growth? So we can calibrate the parameters of our model and get the growth rate of the world GDP using the growth equation. Then we can simulate the climate policy. We can even simulate a very stringent climate policy. In a nutshell, the result is that per capita consumption growth rate may become only insignificantly lower as a consequence of a relatively stringent climate policy. These policy effects have to be compared to the development without the policy. And we know pretty much for sure that without any policy, our prospects are quite bleak, not to mention the disasters and tipping points. And then there are additional issues that can actually help our growth, such as new technologies, momentum effects and expectations, consideration of various risks and uncertainties. And then if on top we add heterogeneous countries and different policies, we'll get even more supportive effects. I'm quickly checking the time. So let me talk about carbon pricing. Economics tells us that if agents have different abatement costs, it is the one with the lowest cost that has to do more abatement. This is pretty intuitive. In the end, abatement will be unequal, and this is simply the efficiency condition. So firms with high abatement costs will abate less, firms with low abatement costs will abate more. What about income differences? rich versus poor. Well, if a rich country abates the same amount as the poor country, its welfare loss will be considerably smaller. Or, in other words, if we ask poor countries to abate the same amount of emissions as in the rich world, we will make them even poorer. Of course, this doesn't work from the fairness and equity point of view. So we need to think about income differences and the associated transfers and potentially different pricing. So what about pricing? Or maybe shall we do an emissions trading? What is the preferred model here? In theory, taxes or emission certificates should produce exactly the same result. But the devil is in the details, as usual. And if we add some uncertainty, for instance, uncertainty about abatement costs, then different conclusions may arise. If we set the price, if we set the carbon tax, but we don't know the abatement cost, it can be either here or here or here, then we will end up with an emissions quantity anywhere in this interval. We have Paris Agreement. We have a temperature target. So we know how much we can still pollute. And that gives us a pretty clear emissions target. And then probably in that case, we might be better off with emissions trading, because there the quantity is set, and then we'll let the market decide where the price will be. So there is no perfect model in the end. Everything depends on what we want to achieve. So let us look at the CO taxes in different countries and over time. Have they been fixed? Have they been constant? Have they been changing? Yes, actually a lot. In fact, they were jumping all over the place. And that means that there is some policy uncertainty. Is it good or bad? Well, from the economics point of view, usually it is argued that policy predictability is important because it sets the target for the agents, they know what to expect. But for climate policy, it might actually be the reverse. And policy uncertainty can support decoupling. Why? Well, if agents don't know exactly what will happen to the carbon tax and where it will be in a few years, they have an incentive to take some precautionary action. So there is some current research going on this topic. So what about the role of policy in the end? What we usually think is the following. Research delivers optimal policy design, and then political sector adopts the ideal policy. But what really happens is something completely different. Research studies problems and proposes policies, public is alert, policy undertakes some first steps, things get in motion, but then new technologies appear on the market. All industries start lobby campaigns because there's some money involved, and policy and public opinion and technology react. Policy may change in a stochastic manner in the end. And institutions matter, of course, in this process. So let me now draw some lessons on decoupling. First, and most importantly, resource scarcity, pollution, and environmental policy are compatible with economic growth. The second one is that dynamic effects of climate policy tend to be either ignored or misinterpreted or sometimes underrated. People often forget about the so-called double dividend. What does it mean? Well, it simply means that if the climate policy is implemented, then the government will collect some proceeds for instance, the proceeds from the carbon tax, and that money can be used for various, for instance, green investments or subsidies, or even reduction of other distorting taxes, or, for instance, income tax. So this is a double dividend. This is the other side of the coin. So in the end, climate policy is actually, or may not necessarily be, as expensive as people might think about it, because there are benefits. In fact, there are double benefits. So we get green economy on the one hand, and we can get tax reduction on other taxes on the other hand. And then there are some other important issues which make the case for decoupling even stronger. As I mentioned, input substitution, which fosters sectoral change. Then environmental risks affect investment and capital accumulation. Then there is, of course, the role of expectations and public policy, which can drive agents' expectations into the right direction. And finally, knowledge diffusion, which I haven't talked a lot about, but if we think about the world consisting of various countries, especially countries with unequal income distribution, then knowledge diffusion can actually help the poor to implement the carbon policy. And once it's implemented, it may actually not, it does not necessarily need to last long. It can be then lifted at some point in the future. It is just important to set the economy on the right green trajectory and, in fact, have decreasing, for instance, carbon taxes all the time. So, policies for decoupling. In the end, we find that carbon policies affect the growth only moderately. Policies can be designed in an efficient and yet equitable way. Of course, we need workable policies, and stochastic policies may accelerate decoupling. Significant decoupling is needed, of course. But is it impossible? I would say no. It is, of course, very ambitious. Now, what about adaptation? Several instruments are available. First, I mentioned the obvious. It's an economic mechanism, very well known and old. It's called insurance. Then, what else? The new things, smart agriculture. Migration is another option. Climate services. So do these things really work? And if yes, then how? I can tell you that insurance doesn't really work where it is needed the most. Of course, it is needed the most in the developing world, but there, in practical terms, it does not work, and it's only about 5% of population which are willing to adopt insurance. And the research shows that there are many reasons underlying this problem. The main reason is, of course, liquidity constraints. So people are simply too poor and they cannot afford to pay the insurance premium. But then there are also, of course, cognitive constraints, financial literacy, which is lacking, things like that. What about migration? Very difficult. We know there are so many migration restrictions, especially if one wants to move from the developing country to an advanced economy. This is practically impossible. And by the way, the status of environmental refugee is not recognized, so that channel doesn't work either. Smart agriculture, that is a new development, and I think there is a high potential there. But what I would like to mention in the next few minutes is climate services, because I think this is something which really works, and we have strong evidence on that. So what are they? Climate services provide end users with relevant information about upcoming weather and climate hazards. think about forecasts. These forecasts can be at different time scale. For instance, very short-term forecasts of just several hours, or medium forecasts of El Niño Southern Oscillation, or very long-term forecasts. For practical purposes, the short-term and the medium-term forecasts are the most relevant. Of course, provision of climate services is not that easy. It requires systematic weather observations, quality control, lots of data analysis, production of the forecast, but most of all, understanding of the sector and user-specific needs. What exactly people need and how this information can be channeled to them. So, adoption of climate services by users requires that the users are aware of the potential value of the service and that they have sufficient understanding of the product. So we need some minimal level of climate literacy. So I've done some research on climate services myself that was in Peru and concerned two completely different types of farmers, agricultural workers, coffee farmers on the one hand, and then quinoa farmers. Coffee farmers are exposed to a plant disease which is called coffee rust, and they need the medium-term forecasts of temperature, humidity, and rain intensity in order to take some preventive measures, which can then mitigate this plant disease. And quinoa farmers, on the other hand, they're exposed to frost, so they need very short-term frost warnings. And once they have the warning, they can take some action, for instance, set up anti-frost fire to protect their crops. So the user-tailored services actually bear very high potential to influence agricultural productivity, especially in developing countries. They are capable of generating large economic value, and most of all, ensure food security, and not to talk about preservation of biodiversity and things like that. So, of course, we had a model for that, which I think I will skip, but this is kind of a graphical representation of this model, where we tried to replicate the exact farming cycle of quinoa producers, including these random occurrences of frost. I will jump directly to the numbers. So what we found is that being informed about frost increases the so-called relative harvest index, that's how we measured their harvest, by 6%. And that is equivalent to a 10% increase of the harvest of the previous year. That 10%, what does that mean in money terms? That is equivalent to about $18.50 per household, or $38.50 per hectare. Maybe these numbers look small to you, but think about people who live on less than $2 a day. So for them, these are quite substantial improvements. However, what we also found is that these numbers correspond to only to a forecast with a skill of only about 40%. That means there is a huge potential for improving the forecast quality. In fact, if the forecast had a perfect skill, the gain to the farmers would be somewhere in the magnitude of $80 per hectare instead of $38. What about new technologies? I really think that there is great potential there. For example, new communication technologies capable of functioning in the wild can be used for really hyper-local forecasting. So the goal is to tailor the product to exactly the right user, or the user will get exactly the right information about the upcoming hazards. And there are currently technologies capable of delivering that. But most of all, I think there is still an unexploited potential for coupling several adaptation mechanisms together. For instance, bringing together insurance and climate services and these new remote sensing technologies. I think that can really deliver substantial benefit to farmers, agricultural workers, especially in the developing world. So I think I will stop here. I thank you for your attention,